All right, well, good afternoon. It is Thursday, 12 to 1, Math 123, and it is February 28th. So today is session 7. We're looking at section 8, which is about scatter plots and linear models. And I just want to remind you about assignments. So we have, assignments due tomorrow are web work number 7, and then the Excel absolute and relative change assignment and the discussion board number 3. So those are all due tomorrow. And then the assignments for today that are due next week are web work number 8, the Excel trend lines assignment, and discussion board number 4. And like I said earlier, exams are all graded, scored, and put in, and then the projects will be done soon. All right, so we're going to get started right away here and look at section 8. And it starts at page 89 and goes through page 105 or 106, somewhere in there. So if you have your book handy, that would be awesome today. So let's start off here with page 90. It says here we're going to talk about linear correlation. And linear correlation is a statistical study relating two variables often report the length of linear correlation between variables. A correlationship is just a relationship between variables. And one thing you want to know is that just because there's a correlation between variables, it doesn't mean that one determines the other's outcome necessarily. And we'll look at that in a little bit here. It means that one doesn't cause the other to happen. So at the bottom of page 90, there's a correlation relationship and a causation. And just know that correlation doesn't imply causation. All right, so it says the positive correlation is when data follows a positive trend, and negative correlation is when the data follows a negative trend. So positive means up and to the right, negative means down and to the right. All right, so how is my voice now? Better? Okay. So let's see. So the positive correlation is a trendward up to the right. A negative correlation is a trendward down to the right. And then it says the strength or weakness of the correlation is determined by how clustered or widespread the data values are from a straight line. The closer all of the dots are to the line, the stronger the correlation. So there's some pictures there. A strong positive correlation, moderate positive, no linear correlation. See how the dots are all scattered about. You can't really draw a line, a best fit line through that cloud of dots. And then a moderate negative correlation and a strong negative correlation. So we'll be looking at some trend lines. These black lines are trend lines. And just identifying them as positive or negative correlation, and if it's strong or moderate correlation. So it says the trend line, so this is over on page 91. The trend line, also called a regression line, for this data set is y equals 0.246x plus 224.85 and has been added to the graph below. So the graph was originally all the dots, those are all the data points, and then we can computer generate a best fit line or a trend line or a regression line for the linear model. It's a linear model because it's a straight line, and we can actually even have the equation, we can have the computer generate the equation for us too. And so it says this represents a linear model and can be used to estimate CPI, or the Consumer Price Index, based on the number of months after the starting point of the data, January 2011. Excel does calculations to draw the line that is closest to all the points on a scatter plot. If another data point was added or removed, Excel would calculate a different linear model. So it would change the orientation of that line. Now I want you to notice this graph. Notice how the months start at 0. This is the months after January 2011. So we're counting from January 2011, which is this dot right here, and then the months after it. So when we put the value in for the x, that x is representing the number of months after January 2011. So x is the values along the horizontal, and y is the value along the verticals. The Y is the consumer price index value. So if we flip back to page 89, it asks these two questions. It says the independent variable or variables are all the values found along the x-axis, the horizontal axis of a graph. What is the independent variable and why might it be called independent? And of course, the independent variable is already underlined. It's the months after January 2011. And it says, why might it be called independent? Well, think about what it is. It's a time unit, right? And time is independent of basically all other things. Time it's not dependent upon anything else. Now, the consumer price index is the dependent variable. And of course, it is determined, the value isn't actually determined by the time, but the value correlates with the time. So the value depends on what month you're talking about. So if I wanted to know about March of 2012, I would just go that many months out and then look up the dot, and that's what the CPI is. So these CPI values they've already happened. So they're not actually controlled by the time, but we look them up and they're defined by the time. So now let's go back to page 91. Page 91 has some problems on there that wants us to look at what's happening and identify some different pieces. So it says find 224.85 on the y-axis and what happens at that point, and where does that value appear in the linear model. So let's take a look. 224.85. Right there. Where does it appear on the linear model? Or excuse me, where does it, what happens at this point? Well, if you look at that point, this black line, the trend line, crosses the y-axis. So that's where the trend line crosses the y-axis. And it says, where does that value appear in the linear model? So the linear model is up here. Notice how that value appears at the end. Okay, so let's see. We found the 224.85. What happens there? That's where the trend line starts. So it's the starting point. And the value appears at the end of that linear model. Those are important ideas. You'll see that as we go along. The linear model begins with 0.246x. This means that CPI is increasing 0.246 is about a quarter, right? 25 cents for each month X after January 2011. And it wants to know what CPI value the model predicts for January of 2011. So I want to make a statement here about this value 0.246. That is called the slope of the line. And when you are asked to discuss or explain or describe the meaning of the slope of a particular graph or line, don't tell me that it's the rate of change. It wants the actual interpretation. So like this. So without the x on it, the 246 is telling us that the CPI is increasing by 0.246 each month after January 2011. Where did all that information come from? Well, it came from the graph. So the 246 is right here. The slope is increasing because the black line is going up, right? So it's increasing by how much? That 0.246 is the how much and when. And the when is down here, each month after January 2011. So all that information is identifiable from the graph. So it wants to know what CPI value the model predicts. Well, let's put it in there. So January of 2011, how many months after January 2011 is that? If it is January 2011, it's 0 months after January 2011, right? So we're going to put a 0 in for the x value in that equation. So if we're going to use the equation or the linear model to make a prediction, all we're going to do is put the value in for the x in. So the x is the number of months after January 2011. So January 2011 is the starting month, so it's month 0. And the value is, of course, 224.85. The next question says, how would we use the linear model to calculate an estimated value for February of 2011? What do you guys think? Thanks, Brian. Yeah, we would put a 1 in for the x. So we would write this equation out. Y equals 0.246 times 1 plus 224.85. And we would just, 0.246 times 1 is just 0.246 plus the 224.85. And that is in dollars and cents. We have to round to the nearest penny. And that looks like $225.10. And then let's look at this last one related to this set of problems. Use the equation to estimate the CPI for January of 2016. So go ahead and do that. Take a minute here. How's that, better? My gosh. Sorry. So, okay, so I got to figure out where I lost you guys. So I think I lost you guys right about here, okay? So the scope of the model is basically your independent variable, how far does it go? And it goes from 0 to 63 months since January of 2011. So there's 60 months is where this green arrow is, where that green arrow is, and then 61, 62, 63. So 63 months. And then it says, would it make sense to estimate the CPI in the year 2030? And the answer is no, because 2030, I mean, this is 2016 right here, right? 60 months is 5 years. So 2030 is way out there, and we don't know what's going on out here because the model ends right there. We don't know if these dots are going down like this real steep, or if they're going up real steep, or if they're steadying off. We don't know what they're doing. So we cannot make a prediction out past 63 months. So that's about all I said. Sorry about that. And so, I was looking at the question in the chat box, and in the chat box, someone said, why do we use 60 months on that number 3 instead of 59? Or, why is this a 60 right here? And so we're not looking at the months between the Januaries, we're looking at the months since the first January. So if we count them, we have February, I'll just make tick marks. February, March, April, May, June, July, August, September, October, November, December, and then to January of 2012. So we would do the same thing for 2013, 2014, 2015, down to 2013, 12, 13, 14, 15, to January of 2016. It's going to be 12 times 5, so there are 60 months because we're counting the January of 2016 in there because that's where we're ending. So that's why it ends up being 60. All right, so questions so far on page 89 to 92 before we start looking at the linear model in more detail. All right, all I hear are crickets chirping, so let's look at page 93. So on page 93, it says the slope of a linear model. Consider the graphs below. Take note of the similarities and differences between the two graphs. And so if we look at these two graphs, they're similar in the fact that we're looking at the total price versus the number of gallons purchased. And the trends are positive, right? Strong and positive. They're all exactly on a line, as a matter of fact. And the only difference really is the steepness of the two lines and the titles. One is for 2% milk and one is for organic milk. So notice here, for 1 gallon of milk, it costs $3.30. For 2 gallons, of course, it's twice that, right? 330 times 2, 330 times 3, 330 times 4, 330 times 5, 330 times 6. Over here, it looks like it's $6.49 for that first gallon. $12.98, of course, 649 times 2 for 2 gallons, and so on. So we can see the steepness is almost twice as much, 330 versus 649. So it says here, notice 649 is greater than 330, and as a result, the organic milk line is steeper than the 2% line. The steepness of a line is commonly referred to as the slope of the line. The slope is simply the unit rate of change, in this case, the cost per 1 gallon of milk. So the unit rate of change means the absolute change in the vertical divided by the absolute change in the horizontal. So if we look at that example there, it shows the 6 gallon minus 5 gallon, and this looks like it is for the organic milk. So 6 gallons cost $38.94, 5 gallons cost $32.45. So that's where the top two numbers came from, the one further to the right in time minus the one to the left, and then 6 gallons minus 5 gallons. And that gets us $6.49 per gallon. So it's a unit rate. As a matter of fact, we could take any two values. We could take the 4 gallon price minus the 1 gallon price. So let's go ahead and do that just so you can see. $25.96 is the 4 gallon price minus the 1 gallon price, and then divided by 4 gallons minus 1 gallon, because that's where we are down here. So if we do that, I'm going to grab my calculator here, and let's see. 25.96 minus 649 is $19.47. 3 gallons, and then we want to make that a unit rate, so we're going to take 1947 and divide it by 3, and we get 649. So it doesn't matter which two values we take. We're taking the right value minus the left one, though, for the y, the dependent variable, over the independent variable. So the up and down one over the left and right one. So it says here the slope is called m of a linear model and can be calculated from the ratio of absolute change in y to the absolute change in x. The slope represents the unit rate of change. And then there was that example. So the slope is an important idea, the rate of change. How steep the line is, the bigger this number is, the steeper the line. And on page 94, it moves us to the next idea with a linear model. And that is the Y-intercept. So since in the case of purchasing milk, both graphs begin at 0. If you were to purchase 0 gallons of milk, you should be paying $0 for the milk. However, let's assume that we are going to the store for more than just milk. We have a cart full of groceries. The last thing on the list is milk. Notice how the additional purchases impact our graph. So now our graph starts up here at $54. Why does it begin at $54? Yeah, that's the cost of all the other groceries, right? So that's the cost before the milk for the other groceries. Notice how 1 gallon of milk purchased, it goes up by $3.30, right? So the line is increasing by $3.30, just like up above on the left, just like this one. It doesn't look as steep though because we're counting by tens on the left-hand column this time. So it says here the y-intercept, often called b, is the point at which the graph crosses the y-axis. B is also the y value that corresponds to an x value of 0. It's a starting value. So that's an important idea, that the b value is the y value that corresponds to an x value of 0. So it's where our line here crosses the 0, the y-intercept. What is the y-intercept for this model? Well, we already determined that. It was $54, right? And it says, what was the y-intercept when we were only purchasing milk? Well, that was 0 because the total cost of the groceries before the milk was $0. So what we're going to do is we're going to take a few minutes here and we're going to put all this together and construct a linear model. So a linear model has this form: y equals mx plus b. Y is the final amount, m is the unit rate or the slope, x is the quantity, and b is the starting value. So when we write a linear model, the y and the x are going to remain. The m and the b are going to be replaced with numbers. So the numbers we replace them with, the m is the slope and the b is the y-intercept. So let's look at the weight loss example on page 95. It says here, David weighs 240 pounds and sets a weight loss goal of 2 pounds per week. Now, before we even read any of that, let's just think about this. If he's losing 2 pounds per week, is the graph of his weight going up or is it going down to the right? It's going down. So there's a negative correlation, or there's a negative slope. So we know the slope is going to be negative. Now it says here, David weighs 240 pounds and sets a weight loss goal of 2 pounds per week. So what is the starting weight, or what is the starting amount? 240, right? So remember that the starting amount is the y-intercept. The rate of change is the slope. So the starting amount is 240 and the rate of change is 2 pounds per week. So when we see this word here, that's our signal that that number around it is the slope. So let's look at this now. Let x represent the number of weeks. Find the linear model which represents how much David hopes to weigh after x weeks of the plan. What will the dependent variable be? Well, the dependent variable is the weight, right? We're examining his weight, and it wants to know what the units are going to be. The number of pounds. What will the independent variable be? The independent variable is, well, the unit is weeks. But we want to be a little more general when we talk about what the independent variable actually is. The independent variable is the time on the diet. And it's represented in the units of weeks. So we already answered letter C, the y-intercept would be the starting point. That's his beginning weight, 240 pounds. The slope, now it says the rate at which y changes when x increases by 1 week. And is it increasing or decreasing? So the slope is 2 pounds. And is it increasing or decreasing? It is decreasing, right? He's weight loss. So 2 pounds decreasing. So the slope then is -2. The negative represents the decrease. Put the pieces together and write the model. So remember that we're going to keep the y and the x. So y equals, we're going to put the slope in front of the x, -2 times the number of weeks plus the starting weight. So that is where the pieces go. Now when you write the slope, remember it's just a number, it's not the x with it. But when you put it in the model, that's where the x goes, it goes with the slope. So it says, how much does David hope to weigh after 4 weeks? So remember that the x represents the number of weeks, the time on the diet. So let's put that in there, -2 times 4 weeks plus 240. So let's see, -2 times 4 is -8 plus 240, 232 pounds. Okay. Now, after 10 weeks, so let's do this without doing any math. Let's, writing it down. Let's just talk about it for a second. 10 weeks, if he's losing 2 pounds per week and he does this for 10 weeks, how much weight did he lose? He lost 20 pounds. That's right. So if he started at 240 and he lost 20, where does he end up? 220. Let's check. So we have -2 times 10 weeks plus 240, and it is -20 plus 240, so 220 pounds. The next question is quite a bit different. It says, how long would it take David to reach his goal weight of 180 pounds? So now we're trying to find out what X would be. And we have the goal weight, we have the total 180. So here's how it would look. Yeah, we're going to put the 180 as the Y and try and find out what the X is. Now there are lots of ways we can do this. I'm going to talk about 3 and show you 2. Okay, so the first one I'm going to tell you about is we could take 40 and we could subtract 2 and keep doing that until we got to 180 pounds. And we count the number of 2's that we subtracted, and that would be the number of weeks. But that would be kind of long to do that. Another thing we could do is we could say, okay, he weighs 240 pounds, and he wants to get to 180. So what's the difference in there? How many pounds does he want to lose? He wants to lose 60 pounds, right? Well, if he's losing 60 pounds and he's doing 2 per week, we would just take 60 and divide by 2 per week. We would get 30 weeks. So we could do it like that. Another way we could do it is we could do it actually doing it algebraically or mathematically. And I'll show you how to do that just so you have this option. So we would do it by solving the equation. And when we solve an equation, what we do is we want to isolate the variable. We want to isolate this x. So it says plus 240, so we would subtract 240 so that we can get the x all by itself here. So we have to do it to both sides though, because the equations are balanced and we want to maintain the balance. So we get -60 equals, so that's from this side over here. And then this is on this side, -2x. And now -2x really means -2 times x. So the next thing we need to do is we have to undo the multiplication. -2 times x, we would divide by -2. Because what is -2 divided by -2? It is 1x. 1, so 1x. But if we divide on the right side, we also have to divide on the left. So -60 divided by -2 is 30, and we get 30 weeks. So whichever method works best for you, that's what you should do. Just make sure that your answer makes sense. Now it says complete David's graph. So he would be, let's see, 30 weeks, he'd be 180 pounds, so that's down here, right? 30 weeks, 180 pounds. And so his graph would look like this, right? Nice straight line, basically. Mine's not that great, but a nice straight line. So there's my straight line. That's what his graph would look like for his weight loss plan. It says if David were to raise his weight loss goal to 3 pounds per week, how would the model in the graph change? So let's think about it. He's going to lose 3 pounds per week. So if he wanted to get to 180, if you wanted to lose that 60 pounds at 3 per week, how many weeks would it take him? It would take 20 weeks, right? So that means he would be at 180 at 20 weeks instead of 30 weeks, starting off in the same place. And this line would go like this. And I think I saw one or more of you mentioned that it would be steeper. And it is steeper. It's more negative. It's negative faster, decreasing faster. So let's see how the model would look. The model would be y equals negative 3x plus 240. What do you think about that last question, number 7? Brian says no. Stephanie says no. Oh my gosh, all these no's are coming in too fast. So why no? Why do you say no? Why isn't it reasonable? I mean, wouldn't it be great to lose 3 pounds a week? Yeah, he would disappear, right? You can only lose so much. You can't lose all of your weight. Yeah, so no, it wouldn't be reasonable. Oh, because of this word right here, right? Indefinitely. Because eventually the weight would go to 0 and then it would be in the negatives and you can't have a negative weight. That wouldn't make sense. So good observation. All right, so I want you to know that on page 96 in your book, it shows you how to make a scatter plot. Okay, shows you how to make a scatter plot. And on pages 102 and 103, it shows you how to take that scatter plot and put a trend line and get the linear regression equation or the trend line equation. It shows you how to do that step by step. So you can do that for your trend line assignment, your Excel trend line assignment. Okay. So let's look at another example here with breast cancer mortality. And we'll do this one together and then I'll give you one to do on your own. Okay. And then, yeah. So let's see. We have this graph here and it has the mortality rate per 100 on the left. So that would be like a percentage. And on the bottom, it looks like it's the year. It has our regression line equation up there, our model, y equals negative 0.1351x plus 276.25. Now remember earlier we said that this number here at the end is the Y-intercept. And the Y-intercept is where your trend line has an x value of 0. Now look at this. This trend line has an x value of 1975 at that location. So that technically is not the Y-intercept. That would be 276.25 if it were, and it's not. It's basically 9. So one of the ideas here is when these two numbers match, then what you're doing is you're just putting in the value down here. But when they don't match, excuse me, let me say that differently. When these values match, you're counting from the left. How many spaces is this? And that's how you determine what value goes in for the x. And that's what we did on that previous one. Let me find it here. Remember, we counted 1 gallon, 2 gallons, 3 gallons, and that would be the value that went there. On this other one, we were counting the weeks, right? 1 week, all the way to 20 weeks, or all the way to 30 weeks, and that's what was going in this spot, because the starting point here was 0. Now the starting point is not 0, and so we are not going to count the spaces after the starting point, like we did those months, remember in the beginning? We did those months after January 2011. We're not doing the years after 1975. We're actually going to put the exact year in. And so let's see, what is the scope of the model in years? Where does it start and where does it end? Okay, I'll answer your question in just a second, Anna. So the scope of the model is 1975 to 20, let's see, this is 2010, there's 2011. So the scope goes from the first data point to the last data point. Even though it says 2015 out here, the data ends at 2011. We don't know what happens after 2011. It could go down real fast or it could go up real fast. We don't know. Okay. So the scope of the model is just however far the X values actually go. All right. So Anna's question was, why is this 276.25 when it's a 9 over here, right? Is that your question, Anna? Why don't they match? Well, they don't match because of this 1975 right here. If we took this all the way to year 0, this would keep going up, right? And it would match that 276.25. Because remember, the Y-intercept is when it reaches the 0. There's the 0. So this point up here would be 276.25. The graph's a little bit deceiving because it ends at 1975. So you have to be careful that you don't call this 276.25 the Y-intercept of this particular graph. And you don't call 9 the Y-intercept of the equation. So 276 is not the intercept of this graph, and Y is not the intercept of the equation. 276 is when you take the year all the way to year 0. Okay. This graph does not have a special name other than it's just the breast cancer mortality in Indiana. So a lot of times when you see data in real life, it's not going to have part, it's going to have part of it missing. Like you might see a graph that looks like this, and it says 5, 10, 15, 20. So it starts at 0 here, right? Down here. But this might be 110, 111, 112, 113, and it might look like it's steep, like it might look steep like this, but when in actuality it might look like there's a big change. But if you look at the whole graph, starting at 0 in both directions, you have this dot here, 5 is right there because it's only one higher, and it's really not very steep at all. So we're only looking at this one portion of it, and it makes it look dramatic when it really isn't. And so a lot of graphs, if you look on the internet or in the newspaper and you're catching some articles, they make them that way to try and make their point, and they're a little bit deceptive about it. So you have to have a good understanding of, okay, if that 0 is not in there, I'm only looking at part of the graph. All right, so number 2 says, how would you classify this correlation? Strong positive, strong negative, moderate negative, moderate positive, or no correlation. So we could say moderate or strong. See, if we take it all the way out to year 0, remember we're only looking at 35 years here compared to the whole 2,000 years, right? So we're only looking at a small part. So it probably is a strong negative correlation. And we would say it's a strong or moderate negative linear correlation. And that's because we want to make sure we're saying it's a linear correlation because it's a straight line. So number 3 says, could you say that the passing of time is causing mortality rates to decrease? Is the passing of time causing mortality rates to decrease? What are your thoughts? Megan says no. Anna says no. You know, it looks like, it looks like it, doesn't it? I mean, as the years go by, the mortality rate's going down. But the question here is the passing of time causing the mortality rates to decrease? And the answer is no. What's causing the mortality rates to decrease? It says explain. Sure, yeah. Medicine, right? Over the years, there's been, more early treatment, early detection, so better medical care. Absolutely. So this is just to reiterate the point I made earlier, where just because there's a correlation, it doesn't imply causation. So just because there's a linear correlation that's strong, it doesn't mean that the passage of time is causing the mortality rate to go down. It's from other factors are causing it to go down. So once it's to estimate the mortality rate for 2001. So again, here we're just going to put the straight year 2001 in. And if we put in 26, which would be 26 years after 1975, we'd see that the percent would be 250-ish, or it'd be 270. It'd be like 270-ish, and that's not really going to match up with the value here at 2001. And so we have to put the actual year in, negative 0.1351 times 2001 plus 276.25. And when you get your answer, just check and see if it makes sense. If it doesn't make sense with your graph, then you know something's wrong. All right, so I just popped it in my calculator and got 5.9. So let's look. Here's 5 and 7, and the dot is right up here. It's close to 6, close to 7, isn't it? Notice that our line is below the actual value. So it says here, how does this compare to the actual mortality rate for 2001? And it's actually lower. So the prediction is lower. We can see that from the graph because the line is actually lower than the dot. If we looked at the value right here for 1979, and we put it in the equation, 1979, we would get a higher value than the actual because the actual is lower than the line. And it says use the linear model to predict the rate for 2015, and will the model be accurate? So let's predict it for 2015, and then we'll answer the second part of this. I got 4.0. And it says, will the model be accurate for 2015? And that goes back to the scope of the model. Now, where is 2015 versus the data? (2015) is out here. There's no data out here. We don't know what's going on. Maybe something could have happened and the mortality rate went up significantly, or maybe there was a really good advancement and it went down dramatically. We don't know if it stayed steady on that line. So we would say, no, it wouldn't be accurate. And it's an estimate. Oops, estimate. That's an M in there. It assumes that the model keeps on going in the, exactly the same, and we don't know if it does or not because the model's only good until 2011. Well, I was going to have you do this one on your own, but we don't really have time, and so I'm just going to run through it with you. I love to give you guys independent practice, but it's just not going to work out here. I told you we had a lot to do today. But go through it with me if you would. I'll just ask the questions and you help me by answering. So it says leasing a particular car costs $850 plus a monthly fee of $225. Create a model that gives the total cost for a given number of months leased. So that tells us right away what we're going to have here. The total cost is what we're trying to get as the Y, and the number of months is the X. So this first question, what will the dependent variable be? That's the cost of the lease, measured in dollars. The independent variable X, the time of the lease, and measured in months. And again, this is on page 105. What is the starting value? So help me out with this. What is the starting value? Like when you go there, you got to pay this up front, and it doesn't change. Yeah, you have to pay the $850 up front. That's not the monthly amount. That's the fixed amount. Okay. So the fixed or the starting amount is the Y-intercept. Remember that. So it's then what's left? The slope. How much is it going? It's increasing $225. So the cost increases $225 every month. And then put the pieces together. So go put the pieces together. Remember the Y and the X stay in there. Those are variables. So what comes after the equals sign? Put it in the chat box or say it out loud, either way. Yes, 225 comes after the equals sign, and then our X, and then plus the starting amount, just like so many of you put in. And then it wants us to put in 6 months. Y equals 225 times 6 months plus 850. And let's see what that is. It is $2,200. And the last question, how many months? So this is asking us now to find the X if the budget was $3,800. So now we're putting $3,800 in, and we're trying to find out what X has to be within our budget. So if we have $3,800 in our pocket, we have to give them $850 up front just to have the opportunity. We're going to subtract $850 from the $3,800, and then we can divide the rest by 225. So 2950, how many times does 225 go into that? Megan says 13. Let's see. Divide by 225. So let's see. I got 13.1 when I divided. So the question is, how many months could you lease the car if your budget was $3,800? And those of you who did say 13 are correct, because you can't lease it for 14 months and 3 days, or whatever that would be. It would be, how many months can you pay for? You can actually pay for 13 months. You could have done that by taking 3,800, subtracting the 850, and then subtracting 225 enough times until you got down to your $0, and you could subtract 13 times. So whichever way, guess and check, you could just have put a 10 in for the X and said, oh, okay, do I have any money left over if I put a 10 in? And found out, and then gone up a couple months. So lots of ways to do that. All right, well, I'm going to end the recording there and then answer some questions if you have some questions.